All right, thank you very much. Hope everyone's having a good morning here so far. So like you said, my name is Noah Kantrowitz, and I'm going to talk about building composable services. So this talk is going to cover four main aspects of building composable services: what they are, why you would build them, how you'd build them, and a couple of the major pitfalls involved in running composable services. So first off, what are composable services? What is a function? Let's start way at the beginning. A function, in the mathematical sense, it's an operation, takes some input, and it produces an output. Idempotence, another important concept. Idempotence is the idea that a function, if called twice, doesn't change its output. So this is important when you're talking about operations that might be run one or more times. If somebody clicks login twice, they should be logged in, not logged in twice or whatever that would mean. It should be the same result no matter how many times they click that button. So then what does composable mean? Composability is a property of functions where you can use the output of one function as the input to another. Pretty common pattern, most applications built this way. You pass data around. This works very nicely with an object-oriented style. But really the fun part of this is when you start applying the idea of composability across a network. So rather than having one big application with code modules for different subsystems, you instead have lots of little services that are cooperating across the network. So why would you do this? Single biggest reason is availability and fault tolerance. A failure can bring down a service. This is a universal truth of infrastructure, but if you have the system divided into lots of tiny services, the ones that aren't part of the failure can continue operating. So for instance, if your search service goes down, the search box on your website might be disabled, but people should still be able to log in, buy things, etc. You can also scale up services much more easily. So because each service is broken out into a separate application, if say your search service is starting to get overloaded, you can just spin up more of them behind a load balancer and keep on going. So testing is also an important piece. The complexity of testing an application goes up exponentially as the size of it increases. So having a lot of small services makes them much easier to test. And finally, logistics. As long as the APIs are agreed upon between the different microservices, the teams that operate them can operate independently. So they can deploy, they can roll back, et cetera, without having to affect all the other teams. So now let's look at how. There's a lot of little things that contribute to the success of microservices as a concept. So while you can use anything to build small services, there are some tools that are easier than others. I'm going to mostly focus on HTTP and REST, as those are fairly common, but they're by no means the only way to do it. So these are the most popular frameworks in each of their respective languages. They all share a couple of characteristics. They have simple APIs. They offer fairly basic URL routing, mostly aimed at REST or REST-like services. They usually issue complex template rendering in favor of making it very easy to return JSON, and they don't usually have deep integration into a particular database or ORM system. And as most of our services are going to be making HTTP requests to other services, and they're going to be returning JSON instead of HTML, really all of those simplicities just save us unnecessary complexity. So like I said, HTTP and JSON are the most common, but there are a couple of alternatives. 0MQ and nanomessage are a more compact wire protocol than HTTP, and protocol buffers and Cap'n Proto are more complex message serialization than JSON. So you should take a look and figure out which one will work best for any given application. So I mentioned most of your services will consume data from other services by HTTP requests, but eventually some of that information does need to actually be stored somewhere. So just like we build models in our web applications to wrap the complexities of the database interactions, in a microservices world, in a composable services world, we instead build model services. So those are services that wrap around a specific database or storage layer, and they provide an interface out to the rest of the network to access the needed information. This keeps the surface area between the services in the database to a minimum, which helps with testing and isolation. The specifics of different databases are beyond the scope of this talk, but I will mention briefly that AP databases, because they are by nature distributed, work very nicely with a distributed service approach. So things like React and Cassandra should definitely be heavily considered for this kind of approach of building services. But you can use anything you want. Conventional wisdom in many web development circles is to cache early and to cache often. I'm here to tell you down this path lies madness. Each of these caches should be considered its own database effectively. So all of the same issues you would have with databases, you will instead have with the caches. High surface area, high contact area between the cache and the rest of the network. So there, you will occasionally run into things that are too slow to compute on the fly, but too big to store. For those, again, you build things like model services that help to keep the surface area low. So you will have a service that represents a cached operation or piece of information within the system. And it hides that complexity from the rest of the service network. Rather than passing around very large data structures within a network of composable services, you can use a more rich data approach. So this means dividing your data up into little chunks and having links between them. So rather than having the cart information embedded in the user structure, instead just include a link to it. That'll link to the microservice that handles cart-related information. This means that you can have the same data passed around, but you don't have to worry about the differences between ways of accessing information and things like that. And you save on overhead for all the things that need the user data but don't need the cart. They simply don't access that substructure. And as a natural extension of rich data APIs, hypermedia APIs. So these provide structure for some common problems like related objects and pagination. So now you have two services that want to communicate. How do they know where to find each other? Service discovery provides a way for cooperating services to locate each other across a network. One of the most important properties in a distributed system, microservices or otherwise, is self-organization. So the ability of the system to shape itself to some extent. So this allows you to route around minor failures. It allows you to do things like complex deployments and generally have a more interesting network topology because the system can sort of find its own shape as necessary. So an example of this is pretty simple. A load balancer that has a health check against its backends and it removes ones that fail. That is self-organization. The load balancer knows to only route requests to currently healthy backends. DNS is one of the earliest forms of service discovery. In modern systems, this usually takes one of two approaches, either multiple records in a DNS server and then you round robin on the client. So you make one request for something like, give me the host that provides the login service, and you get back 4 dozen CNAME or A records, and you pick one of those at random and you load balance that way. Another approach is to use something like HA proxy or another load balancer service, and as new services come online, they register with their relevant proxy. This is very popular in a lot of cloud frameworks because they provide a hosted load balancer system. The downside of using DNS for a lot of things is in the former approach where you're using a lot of duplicate records. Usually you have to update DNS every time a new service comes online or goes offline, and DNS is usually a fairly manual process in a lot of organizations, so that can lead to a lot of overhead. In the latter approach, you need some kind of system for registering and unregistering with a load balancer. Again, if you're in a cloud environment, most major cloud providers have APIs for both DNS and load balancers, so those really aren't such a big deal there. But if you're building this from scratch, it can be a lot of overhead or complexity. So if you want a more fine-grained approach or control over service registration discovery, Zookeeper is probably the most widely used tool. It is a CP database. So that means it's a key value store that is effectively consistent across your entire network. So it means you can make a change on one server as a new service registers, and it will propagate to all of the other ones in a consistent manner. It also allows high-level operations like leader election and ephemeral registration. So if those are things that you're looking to provide, if you need a single master server or if you need much more rapid control over services registering and deregistering, something to look into. Many services have also grown up in the shadow of Zookeeper. It's certainly old and more than a bit crufty, but the details of these are a bit beyond the scope of this talk. Be sure to check them out. Each of them has different trade-offs, different languages, and different levels of stability. So building a microservice doesn't automatically make them fault tolerant, but it does certainly make it easier to build something that is fault tolerant. Two most important things when making a resilient service are careful control over network timeouts. So if something on the other end of a network connection is failing, either because it's no longer there, or it's crashed, or it's simply backed up and can't respond, you want to make sure that your timeouts are relatively low so you can detect that failure and then do something with it. Now, that something is very often going to be just retry. And an important thing with retries in any distributed system is that concept of idempotence that I mentioned before. So you want to make sure that if you run the same request twice due to a timeout or some other temporary failure, that you're not going to corrupt your database or otherwise do terrible things like the person somehow bought the same items twice. So you want to make sure that your retries are automated, but that they're idempotent so that you don't end up with side effects if, say, the first one actually did succeed, but the response is what failed. Some things are very easy to make idempotent, like say deleting a record in a database by its ID. That's naturally idempotent, you don't really need to worry too much about it. But certain other things need explicit checks, so make sure that you do things like have update times or replay nonces on requests that need them so that you can have more explicit idempotence checking. In this example, you can see we're changing a password, and if somebody changes their password twice in rapid succession, we want to make sure that the second one applies. The first one, even if it ends up delayed or it's sitting around in a retry queue, it shouldn't at some later point override the second password change. So here, just a minor example of using a nonce for that. Above all else, make sure you have a strategy for everything being down. Every single service is allowed to fail, and you need to have some kind of response to that. Now, if the thing that failed, from the point of view of your service, if the thing that failed was a critical dependency, sometimes all you can do is return your own error message and say, I cannot answer your request because, say, my database is missing. There's no way for the service to do anything in that case. But anytime where you can degrade gracefully, you should. So for instance, if a cache is down, maybe you can only return half of a user record, but that's certainly better than none of it, and make sure that you cope with that all throughout the system. As before, if the search box is down, that annoys users, but it's better than the entire website being offline because of a minor failure in an index server somewhere. And when possible, use async messaging instead of direct calls. So when you're doing a direct call, that's a synchronous mode call. So that means that you have to have the response before you can continue processing. Using asynchronous messaging and queuing systems means that you can sort of queue up, hey, an event happened, and I'm going to process this at some later point. This allows the queue to serve as a kind of a buffer between the thing producing the events and the things consuming them. So if there's a failure or an error somewhere down the line, the queue will just sort of back up a little bit, and as long as you've got enough storage space and things aren't happening too quickly, that should generally be okay. It gives you a bit of wiggle room in case of errors. And it also helps keep latency down, that if this is something that doesn't have to happen during the time between the user making a request and the user receiving a response, put that in a queue, let it happen offline from the point of view of the user. Now, that might be several milliseconds later, but as far as they're concerned, they already got their response and they're happy and on their way. 2 quick tool recommendations on that. Again, can't really go too much into specifics, but AMQP is the gold standard. RabbitMQ, most common implementation of that I've seen. Gold standard in queuing systems. Kafka is much newer, but has a very impressive feature set and user base. It is definitely my recommendation for asynchronous queuing in a distributed environment. So on the operational side, microservices have a couple of unique requirements. Compared to traditional applications, they use far fewer resources in terms of RAM, CPU cycles, et cetera. So this pairs very nicely with low overhead virtualization systems like Linux's LXC, FreeBSD jails, or Solaris's zones. Docker and Mesos give nice higher level interfaces to some of these systems, but those are a whole different kettle of fish and a very complex topic. Using containerization also allows you to put very hard boundaries between services. So this helps with the defense in depth strategy. If one microservice is compromised, has a security vulnerability or some kind of remote code exploit, you don't have to worry about that cascading as much. It's certainly not a panacea. Firewalls won't solve everything, but it certainly helps. And it helps keep the services isolated from each other and from the user. And while not a requirement, containers certainly play nicely with immutable deployments. This is the idea that once launched, the container becomes a read-only object. You can no longer update it in place. If you want to do a new deploy, you create new containers and you swap traffic over to them. That idea is generally called a rolling deployment or a blue-green deployment, and it certainly makes deploys a lot less scary because you can always just flop back to the old version, no harm, no foul. Also, immutable deployment makes it very easy to do things like rapid response autoscaling, where you're creating and destroying containers at a sub-second level, things that you can't really do with a more large-scale cloud system where it takes a minute or two to build a new VM. But launching an LXC container takes a couple of microseconds in most cases. So you need more of them, start them. Kill them a minute later, who cares? And as the graph of your services tends to get bigger and bigger, it's common to find clusters of logically related services that share an internal support system. Just like you have public and private functions in a large application, you can use network boundaries and subnet boundaries to enforce things like that in a microservice environment. So you can have an internal structure that is shared by a bunch of services, but that shouldn't be exposed beyond that. If there's a certain team that has a support system, it shouldn't be available to other teams. So you can enforce that with firewalls, with network boundaries, things like that. And finally, let's go over a couple of the common pitfalls and perils in a microservice environment. So one major issue is a cascade failure or cascade overload. This is especially prevalent in caching when you have a very CPU-intensive operation, something that takes a little while to compute. And immediately after a deploy, that server gets slammed with requests because its cache is now cold, so it has to rebuild everything. Very, very common for that to get overloaded, and then it cascades to the next, to the next, to the next, and all of a sudden the entire system is backed up. So you definitely want to have some response to this. Most common is to build in a back pressure system of some kind. So as a service gets overloaded, either it pulls itself out of service discovery, so it's no longer getting new requests, since service discovery is how the things are finding it to send it requests, or a back pressure system at the level of the API responses themselves. So when a service gets an error from its upstream, it should back off, either an exponential back off or something similar, before it retries sending those requests, or it should propagate an error of its own. Move from one application to many can also impact visibility and hinder debugging. So you definitely want to make sure, all of these things are very important in any network, but they are absolutely critical with microservices. Having a good metrics and monitoring system, having error reporters, things like Sentry, things like Graphite, absolutely critical. Centralized logging, because you're going to have effectively, especially if you're using containers, you could have the equivalent of hundreds or thousands of services running on different, quote, servers, even if they're just little containers. But you don't want to have to go and check logs on all of those. That would be impossible. So high quality centralized logging and searching and indexing of those logs, again, absolutely critical. Deploying many microservices definitely increases the complexity of deployments, whereas previously you may have had one code drop to a dozen servers or so. Now all of a sudden you have 50 different code bases scaled across 100 different virtual machines or virtual environments. So you're going to want some kind of orchestration tool to handle deployments, something like Fabric or Rundeck or any of the other various lovely orchestration tools. But that is not a replacement. Documentation and training, especially teams that have to, or services that cross multiple teams, is absolutely crucial. Make sure that teams know how to operate and manage each other's services so that if things go wrong, they can handle it. And really just keep these three goals in mind and you'll be well on your way to building better services and APIs. You want things to be minimalist. You want to have as little data in flight as possible, as little data handled as possible. You want things self-organizing so the network can route itself around failures. And you want it to be fault tolerant. So you want to be able to cope with services being down, deal with timeouts, things like that. Thank you very much. Any questions? A little faster than I expected. Yes. So the question was, what is the recommendation for persisting the user session? Generally, you don't. The user session matters when you're doing something that is based around the user, but that'll usually be decoded in the context of the first service. And then you're not making requests in the context of the current user. You're making requests in the context of this user. Because it's a REST-based system, everything already has an object context on it generally.
I guess persistence was a bad word, but a user accesses the first service. The user is not authenticated. You get redirected to our authentication service to get authorization. How do you manage that across multiple microservices so that each one of them doesn't actually redirect to the authentication service to get this authorization every time?
I mean, they would. Each service that needs authentication needs to know, what do I do? If this is coming in without a signature or some kind of header or cookie, what do I do in that case? You could do that at a proxy level, certainly, or you can do it at each service level. From the point of view of the requesting client, it doesn't really matter. All they care about is they make a request, they get redirected. Where you implement that's up to you.
So the recommendation is for each microservice to perform their own authentication with the authentication service?
No, I would say that they should detect there is no I'm missing authentication data. There's no cookie or user API signature or whatever it is on this. I should do something. And that something is usually either return authentication required, or maybe if you're very friendly, you send them a redirect. Yes.
So when you're thinking about composable services and the differences between using microservices internally and using composed or aggregate services for external APIs, is the assumption that aggregate services or composable services, I don't know which one you refer to them as, would just invoke your microservices on your backend?
Yep, just requests flowing around from one service to the next. Very much like you would have function calls in a large application, you instead have REST and JSON requests in a microservices environment. The difference being that when you call a function, there can be exactly one thing that executes as a result of that. But when you make a web request, we have a lot more powerful technologies to do things like load balancers or other ways of doing failover and backup that you can't do in a function call. You do. This will definitely increase latency, but you can keep that low. If you're on an internal network, the network latency is going to be very low. JSON, relatively fast to unpack, or things like cat and proto is literally instantaneous to unpack. It takes 0 milliseconds to unpack a cat and proto data structure. So, you can keep that low, and the benefits in fault tolerance are usually worth it. trying to convert a monolithic application to something that can cope with half its servers being down, usually not something you can do as easily. Sure.
How long did it take you to create the game?
Which the art? Most of yesterday. As Cliff mentioned, I'm a replacement on short notice, so. Yes?
You referred to, you recommended the central logging for monitoring. Do you mean something like a Splunk?
Yep, Splunk, Logstash. I think Rackspace has a thing that I forget the name of. It's not Marconi, that's their queuing thing. Sentry? Sentry is an error logging service. So similar to something like Splunk, but it's dedicated specifically for logging and cataloging errors. These slides will be available on my website shortly once I get back to some internet. Yes.
So how do you deal with taking this model, making it geographically deployed so that the services reliant on a composable service can then just be configured to go to, here's child called A. No matter where I am, where I've deployed that, can I get the appropriate response for where that located service is?
So that's usually a question of service. So that's the service discovery piece that I was mentioning. When you say, I need a service that does X, you go to your service discovery layer and say, give me back something that I can make a request to. I don't really care where it is. And it's up to service discovery to make sure that it looks at the incoming IP address, or just you'll usually have multiple service discovery systems, like one in each data center. So when they register, they go to the service discovery system in their data center, and when you ask, you go to the service discovery system in your data center, and it self-organizes. System doesn't really know that there's a difference per se. It just happens that way. This can be a little bit more of an issue with stateless ones. It's super easy because you just deploy an extra copy in a new data center and the system doesn't know or care. With stateful pieces, that can be more difficult, the actual databases and the storage layers in the back. Cassandra does have cross WAN synchronization systems. React kind of does, but that's up to the specifics of your database at that point. Yes?
What do you find is the best level to build back pressure? Like say building pipelines between IDs and a queue, like rather than 0 to 0. Did you look for back pressure in the queuing software itself, or is that basically a service framework?
Specifically so the question was, at what level do you build back pressure into the service framework, or at what point do you build it into the system? Do you build it into the service framework or at a higher level monitoring? So it depends. There's sort of two cases. There's one, the one you mentioned specifically with a queue getting backed up, where it's sort of in an external-ish system. You probably didn't write the queuing system yourself. So in those cases, it's usually easier to have it at a monitoring level, where you have an Agios alert that fires if your queue depth exceeds whatever. But if it's if the failures or the timeouts are happening within your own services, it's usually easier to deal with that at a service discovery level, where you can say, if you are overloaded, if the CPU average on this machine or the load average or whatever is over X, unregister from service discovery. And then you have something that's monitoring service discovery and says, if there are less than 5 search services available, either page someone or just start more, or both more likely. So that sort of builds in the scaling as a response to the back pressure is the unregistering from service discovery, and the response to that is the system starts auto-scaling if it sees there aren't enough available services. Any other questions? All right, well, thank you all for coming, and I hope everyone enjoys lunch.